Howdy Eggs, my name is Tony Moma and my screencast is on Microinstructions. First, recall that MIPS instructions take several cycles to complete in a multi-cycle processor, and during each cycle, certain signals must be asserted for it to execute properly. The way the processor will go about asserting these signals is by calling a microinstruction, which will assert the signals it needs at that point in time. But before I go on any more about that definition, I want to illustrate the usefulness of microinstructions with an analogy. Let's pretend it's the year 1200 and person A wants to send a message to person B. However, telephones have not been invented yet, so the only way you can do that is by spreading it from person to person. And the farther person B is from person A, the more people have to spread it through. Obviously, the farther person B is from person A, the harder it will be for the original message to reach person B. Now, fast forward to the year 2000, and telephones have now been invented. So if person A wants to send a message to person B, he can now do so directly. Micro instructions do a similar favor for us, and here's how. Take a look at this state diagram. It incorporates the load word, store word, BEQ, jump, and R-type instructions. If our professor were to ask us to create a finite state machine based on this diagram, it wouldn't be too hard because there are only 10 states. However, suppose we wanted to incorporate the entire MIPS instruction set. Now we're talking hundreds upon hundreds of states now, and now suddenly creating a finite state machine is not so feasible. Now, here's how microinstructions rescue us. On the right side of the page is a block of memory, and at each address in this memory is a microinstruction that corresponds to a state on the state diagram. So what the processor does now, whenever it's in a state, whatever state it is in, it'll call that corresponding microinstruction that it will assert the signals it needs. So for example, if we're in state 0, what the processor will do, it'll go to the address memory 0, execute the microinstruction, and then that'll assert the signals needed for that instruction. This is great because now if we want to incorporate the entire MIPS instruction set, all that means is that now we just need to add more micro instructions. That's way more simpler than how if we were trying to do that with a finite state machine, where more states means more wires and more flip-flops and all of that complicated stuff. Now, the only rule to follow here for addressing micro instructions is that if you're in a state that only has one possible next state, then the corresponding micro instructions must be next to each other in memory. For example, if you look at the state 0, fetch can only go to decode. It can go nowhere else. As a result, the corresponding micro instructions are adjacent in memory. So that's the one rule to follow. For state 1, there's 4 different states you can go to, 2, 6, 8, and 9. So the rule does not apply to that. But just recall that if a state A only has one possible next state, then the 2 corresponding instructions must be next to each other in memory. Now, the way microinstructions make this all work is by doing 2 things. Each microinstruction specifies which signals should be asserted for its corresponding states, and they specify which microinstruction needs to be executed next. And it does that using 7 fields. The first field is the ALU control field, which determines what goes on in the ALU. Then there's source 1 and 2, which controls the ALU inputs. There's register control, which controls the register file. Memory, which controls the data and instruction memory. PC write control, which determines how we update the PC. And the sequence field, which determines the next instruction. Here's an example of a microinstruction. It is the fetch microinstruction. In the ALU control field, we set the value to add because during this stage, we want to add PC plus 4. That also explains the values for source 1 and source 2. Reg control is essentially a don't care because during this stage, we're not using the register file. Memory is set to read PC because during this stage, we're fetching an instruction from memory, hence we want to read the address stored in PC. PC write control is set to ALU because we want to write the output of ALU to the PC, a la PC plus 4. And sequencing is set to value SEQ, which simply means go to the next microinstruction in memory. Recall in the previous 2 slides ago, I mentioned how fetch can only go to decode As a result, the micro-instructions must be next to each other in memory. Hence, that's what SEQ does for us. It just takes us to the next instruction in memory. In the label field, which I did not mention in the last slide, now what this field, here's what this field does. Suppose we're examining a micro-instruction that corresponds to the last state of load word. Pretty much the last state of any instruction, the next state will always be fetch, because you want to fetch a new instruction. So what you would do for those micro-instructions, in the sequencing field, you would write fetch. And what the processor will then do, it'll look for the micro-instruction with the label fetch. And when it does that, it'll find this micro-instruction and then execute the signals needed for that. That's what the label field does for each micro-instruction. Alright, more values you can place for ALU control are subtract for subtractions, or func code, which means it'll look at the function code of the MIPS instruction and determine the ALU operation based on that. For source 1, you can have PC, as we saw earlier, for computing PC plus 4, or simply A, which sends the register RF to the input. For source 2, we can use B, which sends register RT to the input. 4, which we'd obviously use for computing PC plus 4. Extend for where I instructions, we want to send the extended 16-bit immediate. Or extend shift, which sends the immediate shifted twice. We would use this for when we want to compute the branch target address. For register control, we have values read, which we do for fetching RF and RT. We do this during the decode cycle. There's write ALU, which writes the output of the ALU to the register file. Our instructions would use this at some point. And then there's write MDR, which writes the output of the data memory to the register file. Obviously, load word would use this. Then in the memory field, we have read PC, which we would use when we're fetching an instruction. We'd want to read the PC address out of the memory. There's read ALU, which reads the value from memory using the output of the ALU as the address. Load word would use that. And then there's write to ALU, which writes to the address in memory. Writes to the address output by the ALU. Store word would use that one at some point. For PC writes control, we have ALU, which writes the output of ALU to a PC. We do this when we're computing PC plus 4. And then there's ALU out condition, which outwrites the output of the ALU to the PC if a condition is met. Branches would use this condition, would use this value. And then there's jump address, which would be used for jump instructions. And then lastly, in the sequence field, you have SEQ, which, as we mentioned earlier, just takes us to the next micro instruction in memory. There's fetch, which takes us to the last micro instruction. And then there's a dispatch signal. Now we use dispatch signals for micro instructions that correspond to a state that has more than one possible next state. What the dispatch signal will do, it'll look at the opcode of the MIPS instruction and then determine what the next state should be based on that opcode. So essentially, you can look at the dispatch signal as a case statement that looks at the opcode and determines what to do next based on that opcode. So for example, look at the decode cycle. Decode has 4 potential next states. So for the corresponding micro instruction in the sequence field, we would put dispatch 1, and dispatch 1 would choose between states 2, 6, 8, and 9, depending on the opcode. So if it detects a load word opcode, it'll go to state 2. If it detects a jump opcode, it'll go to state 9, and so forth. Similarly, we have a similar case in state 2. It'll depending on the opcode, it'll choose between state 3 and state 5 as the next state. So if it detects a load word opcode, it'll go to state 3, and if it detects a store word opcode, it'll go to state 5. And in the micro instruction for state 2, we'd have a dispatch 2 signal. Each micro instruction that uses a dispatch signal has its own dispatch. Hence that explains the underscore. For state 1, we would have dispatch 1 in its micro instruction, and then for state 2 it would be dispatch 2, or whichever arbitrary number. Okay. Alright. So to summarize, each micro instruction specifies 2 things: which signals need to be asserted for its corresponding states, and the microinstruction that needs to be executed next. Microinstructions are useful because they allow us to go from one state directly to another without having the extra added complication of wires and gates and flip-flops and etc. This is great because now if we want to incorporate the entire MIPS instruction set, all it means is we got to add more microinstructions, which is much more simpler than if we were using all those other tools like flip-flops and things such as that nature. And then thirdly is the rule for addressing microinstructions. And it's just one simple rule. If state A can only go to state B, then their corresponding microinstructions must be next to each other in memory. That's the only rule for addressing them. And then lastly, each microinstruction has 7 fields. The ALU control, which determines the ALU operation, source 1 and 2, which controls the ALU inputs, register control, which controls the register file, memory, which controls the data and instruction memory, and PC write, which controls how we update the PC. Oh, and also the sequence field, which determines the next instruction. Well, that sums up my presentation. Thanks for listening. I hope you found this useful and interesting, and I wish you the best of luck in the CN350. Thanks and gig 'em.